Send me the link to the presentation.
You should have an email. All right, let's see. All right, good morning, everyone. We're just setting up here. We'll get started in a couple of minutes. I'll just allow a few minutes for attendees to join. Great. Good morning, good afternoon, everybody. We'll be starting in a couple of minutes, just setting up here. So, yeah, just as a reminder, so today we have Frances Conway, VP Product and Developer Relations at Source. I'll be talking about predicting the future of the Kubernetes code, the Kubernetes project by analyzing the code base. So it's based on an analysis of the Kubernetes code base that we did recently, and excited for him to share the results with you today. So you should have received an email with the link. So in the meantime, a little bit of logistics. So feel free to ask any question you have in the chat. Francis will be taking them as they come in. No worries. And great. So I guess if you want to share your screen.
Yeah, sure. So let's mute you so I'll have the. There you go. Cool. So just checking that people can actually hear me. So if you can hear me, maybe on the chat, say hi or something. Also say hi in the chat. It's always good. All right. I saw Michael. Thank you. Okay, cool. So let me share my screen. Actually, let me minimize my confidential email and then share my screen. There we go. Okay, so the analysis that we're going to be doing today is basically an analysis of the Kubernetes code base. So for those that have never seen it, if you go to github.com/Kubernetes, you're going to see that we have a lot of repositories in there. So there's 68 repositories, the most important one being Kubernetes, which is the one we're going to be concentrating most of the analysis on. But we also have a lot of other repositories and actually even other organizations that we'll mention in a little bit. So I'm going to show you a little bit how is it that I started the whole analysis from scratch. So what we're going to do is we're going to be connecting to, let me remove this so I can see it. I want to show you one of our instances on Google Cloud. You can use anything in here. I'm just using Google Cloud because I know it quite well. I used to work there. And we do have an engine playground. So any Linux machine would work good for you. The first step that we're going to do is we're going to install the source engine. In order to do that, while this is connecting, you can actually find how to install it by going to source.tag/engine, and you will see there's a install engine in here, and you feel this. This is actually a really good job by Victor, and it will send you a link to download the system that you want. So you have Linux, macOS, or Windows. In my case, I already downloaded it, so I already have source. Make it a bit bigger. Source banner here. So if you do source version like this, you will see that we already have some stuff running in there. So I'm actually going to do source purge. Source prune to make sure that we remove all of the possible things that are already installed here. Okay, so next step, what I'm going to do is I'm going to download all of the repositories that I'm interested on looking at. I already did that in here, and if you're curious on how to download all of the repositories inside of an organization, this is actually how I do it. I use the GitHub API, so I have these pages, I go until there's no more pages, and you're getting basically every single time a new API file in there. So let's see what that looks like. That's a bunch of JSON. And then what I do is simply using JQ. I don't know if you've ever seen that. I'm generating from all of the JSON files, I'm extracting the HTML URL and putting that under repos.txt. Repos.txt. And that contains all of the repositories that I'm actually downloading. So that's why you can see that, I can actually not see it because Zoom is in the middle. So there's 67 different lines in here. I don't know if you get to see it. Oh yeah, you get to see it if you don't move the screen, the thing. And then, whoops. Last thing that I do is simply doing git clone. So for every repository in that file, I'm gonna do git clone, and that's it. That's actually how I created this data set. So there's nothing else, no extra preparation that it needs to be done. You just download all the source code, and now you're ready to start analyzing it. So how do you do that? How do you analyze code? Okay, so what you're gonna do is you're going to do source init for initialize, and you're going to pass the folder that contains all of the repositories that you want to analyze. So in this case, we are now at home. So it's actually inside of Kubernetes, there's all of those repositories. So I'm going to run source init Kubernetes. When I do this, this is actually going to install a bunch of different things. And it's kind of interesting to see that when you do source init Kubernetes, it's going to be checking a bunch of different things. Like one of them is the fact that there's a new version available, but also you're gonna see some messages related to Docker. The interesting thing is the fact that the engine, the source engine is simply a little binary that you download, but it's going to be installing things by using Docker. So if I do Docker PS, you will see that I have a daemon running there. So you have this kind of a client server thing going on. So if you want to stop everything, you can do source, I keep on saying prune, but it's not prune, it's source. Oh, it's actually prune. Okay, so source prune, you can do that. Or also you can do Docker prune. That would also work. It would remove all of the things that we have installed. So in any case, your machine will always be clean. Okay, so now we have the instance running. We have our engine running, analyzing the Kubernetes codebase. We can start doing things like source, SQL, and this again is going to install a new binary. So just downloaded a bunch of different images, including Babelfish and codebase, and all of these different projects that are actually the things that we put together and we package into our product, which is the engine. Okay, so now that you're here, let's see if clear works. It does not. No. Okay, so let me go back here and do it again here so you can actually read it well. Okay, so you can do select from repositories. And now you've got a list of all the repositories that we're analyzing. This is always something good to do when you start, just to make sure that you're actually analyzing what you expect. It happened to me a couple of times that I actually initialized it wrong, and then it doesn't make any sense. So this kind of query, it's a pretty useful one to do. Another way to do the same kind of query is actually doing it directly from the command line. So source SQL select from repositories, for instance, it's going to do exactly the same thing, but without having to be interactive. The next way the different way of doing kind of the same thing, which is actually my favorite one, is if you do source web SQL. Now, when you do source web SQL, and actually, let me make sure that I don't have any other things running in there. Okay, that should work, cool. So when you do source web SQL, what's going to happen is on top of the engine, we're actually going to start a new web client that you can use on localhost 8080, assuming localhost is the machine that you're accessing right now. Since that is not the case, we're actually going to use this IP right here. Go to 8080. Okay, now when I do this, again, I get to run all of the things that I'm interested in. So you can do the same. Let's do the same query as before, just to make sure that we're still getting the same behavior. Repositories. You're going to see all the 67 repositories that we've seen already in 3 different ways. One by doing ls in the directory. Another one was by simply doing select repositories from the command line, and now from this client. Now, this client is actually a very good place to start, and I would recommend everyone. How do you remove this thing? Hide video panel. Nope, that's not the panel I wanted to hide. Okay, whatever. There's an annoying thing that covers half of my buttons. So yeah, one more thing that you can do is actually select from files. Now, if you do this, you're going to be selecting all of the files in all of the versions, in all of the repositories, which is actually a lot of files. Even just counting them, it's going to take a while. So instead of doing that, I'm simply going to limit the result by using SQL. So I'm going to say, just give me 10 files. Now, when you get those files, you're going to see the table in here. What are the columns? You can also see them right here on the left side. This is actually pretty useful. You can see that for files, we have the repository ID. The repository ID is actually something we have for every single table. Everything is indexed by the repository ID, which helps filtering a lot of things and actually makes the whole thing much faster. Then we have the file path. So where in this repository is this file? So GitHub.pull something. I think that's going to be pull request template. But we also have contributor.md, go depth, license, etc. Right? Now let's say that also we have the blob hash, and more important, the blob content. The blob content is interesting because the playground actually understands how to handle it correctly. So it will actually open this big thing so you can read it directly, right? So that's clearly a license. You can actually see the content. That works really well. Okay, so now let's talk a little bit more about what are the things that are not part of MySQL, right? Like this is a MySQL instance. It looks like it, but actually it's not because there's no database behind. We're actually analyzing the source code that we just cloned from GitHub. So what is the next step? Okay, so let's say that I'm going to, I'm only interested in all the files that are Go. How could you do that? Well, you could do something like where file path, like, and if I remember correctly, this should be something like .go. And I think they use a $sign. Is it $sign or, oh no, percent, I think. Okay, so percent, that's going to tell you all of the Go files. But actually, it's not all of the Go files. These are all of the files that say they're Go because of their extension, right? What if you wanted to obtain all of the files that are, say, MATLAB? You would do .m, but then you're also going to get other languages. Like you also have Objective-C, you have Mathematica, they also use the same extension. So we have a better way to do this. So what we can do is, so let's say we're going to use only the file path and the blob content. And now what I'm going to say is, and also call the function language, which receives 2 parameters, the file path and blob content. And instead of doing a where on the language, on the extension, you can do that on the language. So in order to do that, you're going to need to name this. I'm going to lang, and then you can do lang equals go. So now this is basically the same idea, and it will return the same things. The difference is that now we know that these actually go. We are looking inside of the file, parsing it, and looking that, indeed confirming that this is the language that we expect. The next interesting thing that we're actually going to see during the analysis, and after this we can start actually analyzing the Kubernetes code base, is the fact that once you have a language, the next step is to try to parse the program, right? And in order to do this, we have this concept. So if you say this Go, the next step is you have this concept here, UAST. And UAST stands for Universal Abstract Syntax Tree. And what it does is it parses the code on the left, and it generates an abstract syntax tree, which is the tree that corresponds as the tree that is the output of parsing a program. You always get a tree that has things like this, the whole file. Inside we have a comment group. Let's see what else we can find. We have another comment group. Then we have, okay, so declarations. We have import statement here, for instance, that is importing github.com SPF13 pflag, right? So basically with these, you are seeing a different way of representing the same code that you have on the left. The interesting part here is actually the fact that this same format, this way of storing the tree is the same no matter what programming language you're using, right? And the important thing about that is the fact that once you have that, then we can store and handle and like transfer all of these content the same way no matter what language you have. And on top of that, we can create libraries. One of the libraries that we've created is what we call the libuast, that allows you to extract specific components, right? So the way you can do it is, it's actually XPath. So if you've ever used XPath, you already know how to do this. If you've never used XPath, it's a little bit like a slightly more advanced version of CSS selectors, really. So let's say that I want to extract all of the things that are Go gen declarations, right? Okay, so let's do that. So you can do that by simply doing Go gen declarations. Now, you got all the declarations in here. So you have, for instance, this also declaration, because it's a declaration, a type declaration. This is another type declaration, another type declaration. Let's see what other declarations we have there. Not type declarations. This is a type declaration too. I guess that in this file, everything is a type declaration. So not very interesting. But the important part is actually the fact that there's one second universal thing about universal abstract syntax trees. There's the fact that, yeah, you can query them in the same way, no matter what they are, but also, and even more important, is the fact that you can query by the universal labels that we use. So for instance, here you have Go comment, but also you have this UAST comment. And this UAST comment is the same no matter what programming language you're using. If you're passing Python or Go or Java, you're always going to have, you have a comment, you're going to have these labels saying this is a UAST comment. Another one that is pretty cool is the UAST string, for instance. So you can say, hey, give me all the strings. So you do a UAST string, and then it's going to point out all of the strings in the code. So here, for instance, you point to that one, or selector, etc. So you can find this quite easily. The interesting part about UASTs is the fact that they are also part of the language or the extra functions that we've added to SQL in order to build the engine. So if you do UAST, you're going to need to pass at least two parameters. The first one is going to be the content that you want to parse. So that is plot content. And the second one is the language that you want to use. And most of the time, it's going to be this. Most of the time, it's going to be the language that you're going to guess. In this case, since we know that everything is Go, we could also just say Go. But most of the time, you're going to actually be doing this. So let's do run query and see what the UAST looks like. Okay, so that UAST right there is going to give you that tree directly. So how do you handle trees from SQL? It's actually not that easy. The way you're going to do is most of the time, you're going to extract the pieces that you care about. So let's say, and that is actually the third parameter, which is optional. So continuing the same example as before, you can say, I want to get all of the strings, and you're going to get all of the strings and all of the nodes and the strings in there, right? But actually, most of the time, you don't really care about the node. You care about the value itself. So in order to do that, you can simply do /value. And now you're getting all of the strings in there directly.
Francis, we do have a question from Abby. Is the UAST by default, or is it created by users?
I'm not sure I understand the question. The UAST is a concept that exists in the engine. So it's from a MySQL point of view, it's a custom function, but it's something that we provide already. So you don't need to do anything. Given any content that you know how to parse, so you know the language, you can call this function UAST and it will return something useful. I don't know if that answers the question. Well, we'll ask. Maybe there's lag or something. So yeah, let me know, Abby, if that answers the question. If not, ask a follow-up question and I'll try to do my best. Okay, so with this now, what we're able to do is we're able to find files inside of a set of repositories. We're able to find what language they are written in, and even parse and extract specific tokens of that. The next step is, okay, so if you go back to the engine website, you will see that one of the things that it does is code retrieval, language agnostic code analysis. Those two, we've talked about them. This one here, we have not talked about, history analysis. What does that mean? Well, what it means is that when you are doing this analysis, here we're doing it for all of the files in all of the repositories and all of the versions. But actually, you can do different things. So for instance, what you can do is, here, what we're doing is we're getting the name of the files written in Go. So we're checking the language, and we're keeping it as language. Then we're extracting the content, and then we're extracting the UAST. I don't really care about the UAST right now. I don't really care about this right now. But the interesting thing is about this from. What we're doing is we're getting all of the files that are, so I don't care about this one. The files that are in a reference. So we're getting the reference table as refs. Let's see, the reference table contains repository ID, reference name, and commit hash. And these, there's many of them. There's one per branch and one per tag on Git. But the interesting thing is that there's one called head, right? And that is the one that corresponds to the master head, to the entrance to the entry point to the repository. So what we're doing is get all the references, do a join with all of the commit files, and commit files are all of the files given a commit. So you're gonna see per commit, we have the blob hash and the tree hash and the file path. So for all the files, we're going to be able to extract the content or where they are. And then we're gonna do the join with the files in here to extract the actual content. So when you run this, you're going to see that, oh, this is actually a lot of files now that I think about it, because we're doing the whole analysis over all of the things. So let's also add an repository ID, so r.repository ID equals to Kubernetes. This should be faster. But the important thing to see here is the fact that as soon as you start working with files, this is going to get larger quite quick. There's an even better way of showing this, which is actually, let's play with one of my favorite tables here, which is ref commits. So when you do select star from ref commits, where ref name equals head and repository ID equals Kubernetes. Let's limit 10 first. Okay, so you can see that these are actually all the commit hashes on the Kubernetes head, starting from 0 and going back in time, right? So if we count how many we have, I think it was 72,000 or so. This is a lot of them. But anyway, with this, basically the idea is that we're going to be able to start doing those analyses that we were doing on head, but going back in time for as long as we want. If you actually want to get the data about that commit, what you would do is get the repository ID and the commit hash and look that up in the commits table, because you have repository ID and commit hash. So actually, this is a good opportunity to use natural union. If you don't know what it is, basically it's a union where all of the columns that have the same name need to match. So if you're doing a union of this table that has ref name and a history index, since ref name and history index are not here, what you're going to be using is just repository ID and commit hash. So you're going to be doing a union on those columns being exactly the same. Okay, so let's actually stop the client. And instead, we're going to do a Jupyter Notebook. Now, when I do Jupyter Notebook, as soon as I refresh, oh, I actually removed it. Let me open this again. Okay, so now as soon as I do this, I'm going to be able to go into the engine analysis and open our Kubernetes analysis. Now, the interesting thing about this is the fact that now we are going to be using the Kubernetes, we're going to be analyzing Kubernetes, all the Kubernetes source code, by using Python and MySQL. And the good part about this is that this is actually nothing new, right? If you know Python and you know MySQL, there's nothing new. We're going to be using the same libraries. So we're going to be using PyMySQL, and then we're going to be generating graphs, etc., with NumPy and Matplotlib. If you look at other analysis, you will see that some of the people might want to use different libraries like pandas, etc. All of these things actually interact very well together, because the idea is that we are integrating the engine as one more data source for you. And then all of the rest of data analysis processes that you might be doing will just work with this. So let's start by running this. Then let's count all of the files. So here what I'm doing is I'm running, let's see, I'm actually counting all of the commits in order. So I'm counting, as I was saying before, find all of the commits that you have, select the, so find only the commit hash, that is the part that we care about, and select only the ones under Kubernetes and inside of head. And I just noticed that actually the instance where I'm running this is not very powerful. So I'm not going to be running all of the queries. Normally, we do it in a very, very large machine, very, very large being, I think it was 64 cores and a couple of gigabytes of data. And in that machine, actually, this operation takes around, I think it was like 4 seconds. The whole thing is running Go, which means that we are utilizing all of the CPUs very well. So as soon as you add more CPUs, everything is going to distribute much better. And even at some point, even like that, even with that concurrency, at some point you're going to hit some scaling issues, and that's when we suggest getting in touch with us, because we also have the distributed version we're working on, which is part of the engine enterprise edition. Okay, so now we know that we have 75,000 commits on head. So next, what we can do is, okay, so given all of those commits, I want to know when they happen, right? So you can actually extract that information running this, and this is probably the last query I'm going to run just to show you that this is real and it works, but you need a larger machine that, I think the one I got only has like 2 CPUs, so that's probably the issue. Now that we've run these two, what we have at the end is a list of all of the commits that we're going to be analyzing and a list of the timestamps. So next, one of the things that we can do is, okay, so find me all of the tags. So tags, as I said before, they're going to be under references. So all of the references that are called ref/tag/something, right? V something. That's how you do it. Basically, this is the .* from Bash. This is how you write it in SQL. So this is going to find all of the references that have a name in this style. Now, if I run this is going to return quite quick. So it actually found a bunch of different ones, and then we can use Pipelet to represent them on time. So now you can see all of the, let me zoom in a little bit. So now you can see that before 1.0, it was kind of an interesting stage of the project where there was new releases basically every week, I'd say. But then all of a sudden, not every week, but definitely, oh yeah, no, every month, the 15th of every month. No, wait, that is the year. That is not the 15th of every month. Yeah, so every 2 weeks or so, there was something new, which is it's pretty intense. And then they went into V1.0, V1.1, V1.2. From V1.2, actually, that 6-month period started to actually show. And sorry, at 3 months, this is kind of a weird way of reading it. Yes, every 3 months, there was a new release, and it's been stable like that since then. Something else that we can do, and this one for sure, I will not be running it directly on this machine because this is a much more intense analysis, is we can count how many files we have per commit. So why per commit? Well, because when you're counting the number of files, what you want to do is count the number of files for a version. Otherwise, you will be counting the number of files for all possible versions in all repositories. So this is why what we're doing is, for all the commits that we had before, we're gonna choose one and we're gonna pass that. We're gonna get all of the trees for that commit. So the tree is actually how you store things in Git. It's going to have a tree of all of the files and all of the entries. And then we're going to check all of those entries, which ones correspond to an actual file. So this is 40,000 is actually a directory. 40,000 is directory. So we don't want to get directories. We just want to get files. We're going to get the ones that are inside of Kubernetes that are in one of the trees that we found and also are not part of the things we do not care, right? So if it's inside of vendor or Go Devs or third party or something internal, we do not care about these files. We're not going to count them. Okay, so now that we've defined these, you could run this directly. And if you run this directly, it's going to take a while, actually, because basically you could run this over 75,000 files. Even if it took 75,000 commits, even if it took only 1 second per commit, this is going to be a while, right? So what we're going to do is actually divide the number of commits in groups of 1,000. So this is going to allow me to do, instead of 75,000 points, I'm going to take only 75 of them. And then I'm going to run those 75 tasks in parallel. If you don't understand how this works, I will just invite you to go see basically how the parallel package from the joblib library of Python. How does that work? Because basically what we're doing is we're just running all of the queries at the same time. So you can see that we are actually running 72 points, and it took in this machine 2.7 minutes. So almost 3 minutes running on top of 96 CPUs, so 96 cores. So that's a pretty large number of cores. If you run this now on this instance with only 2 cores, this is going to take easily 40 times longer, so we don't really have the time. The next step is you end up with this number of file counts, right? So you have counts per commit, and for every commit, you also have the time. You know when that commit was done. So now, with a little bit of list comprehension and pipeline, you can start creating this number of files over time. And you can see that this is mostly always growing, which is what you would expect. But there's some interesting points where it actually goes down, like that peak in there, that peak in there, which means that maybe there's been some refactoring, or maybe a dependency that was not in the good place has been moved into a place where it actually recognizes the dependency, so we do not count it anymore. But in any case, sometimes files disappear. Okay, so what if you wanted to count the number of lines instead of number of files? It's basically the same. The only difference is that we are going to, for every file, we are going to get the content, split it by the number, by the end of line character, and then count the length of that array. -1, because that's how it works. Otherwise, we're getting 1 extra every time. And then sum all of those, right? So here, even if this looks kind of advanced, this is actually completely standard MySQL, right? It's actually standard SQL. You can do this on basically everything as long as blob content is some kind of blob, a slice, an array of bytes or something like that, right? So by doing this now, we can exactly run the same thing as before. This one took a little bit longer, took 4 minutes, because we are actually running not 2, but 3 queries. We're doing that third one there. And now we have the number of lines of code. And this is interesting because the number of lines of code is actually not as continuous as the previous one. There's huge growth here in July 2016. It goes up, and then it goes down again, it goes down again. So there's indeed some refactoring going on, and it's quite heavy. Here, for instance, this is 1, 2, 3, 1, 2, 3. So that is 20 million lines of code. No, 2 million, right? 1, 2, 3, 1, 2, 3. Let's not mess it up with the number. So yeah, it's almost 2 million lines of code. So there's one, yeah, that is 250,000 of lines of code disappearing all of a sudden. So there's something interesting going on in there, but we still don't know. So one more thing that we can do is, by just doing some basic maths and finding the ratio between the values of the number of lines and number of files, we can plug those two together and see that indeed there's certain correlation, which makes sense because the more files you have, the more number of lines you have in general, but not always, right? Like the growth that you can see here in number of files does not correspond to the drop in number of files. So this is an interesting, sorry, the increase of number of files does not correspond to the decrease in number of lines of code. So there's something interesting going on there, and we look at that in a minute. I'm wondering, is there any questions?
Not yet.
Okay, cool. So I'll continue. Okay, so one more thing that you can do to understand the growth or the activity in a repository is just simply analyzing the number of commits. So I run this query where I'm doing, okay, so find all of the commits, and for every commit, extract the year, the month, and the day, and then count how many you get per year, month, and day. So this what it's going to tell you is per day of the year, how many commits were done, right? Then you can do a little bit of pipeplot, and again, print something like this. So in here you can see that there's some activity, and it seems like it might be declining. It seems like it, right? Is it actually declining or not? Well, it's kind of hard to see in here. So we can do it per month. In here, now I'm not even running the query again. I'm just simply doing a little bit of like date mathematics in Python, and I'm able to print it again per month and see that indeed there's some declining. Here, the average in 2017 is clearly higher than the average in 2018. So that is interesting, but what does that mean? Well, it means that since we are counting all of the repositories here, we're not limiting this to the repositories, the commits under Kubernetes. We are actually doing Kubernetes, but also Kubernetes, everything else in there, right? So it could mean that we were working a lot on other projects and we're not anymore, or it could mean that actually Kubernetes is declining. How can we count that? Well, let's count it per month, and then do it per month and also per repository. So now we're grouping by repository. So we're gonna be counting how many commits per month and per repository we have, and then we can plot that. So now when you plot that, you can see that the dark blue color, which I didn't show, but the dark blue color is actually Kubernetes, Kubernetes. But there's still, it's a little bit too messy. There's a little bit too many colors. So let's do it only per year. And per year, we're gonna get a lot of much more useful information. So here you can see that the blue here is actually the Kubernetes is the main project. So you can see that it's somehow increasing. Maybe, maybe not. It's kind of hard to see. And then there's a bunch of different ones. So let's limit it to the 10 top ones, or to the 5 top ones, actually. And now we can see very clearly that the activity on Kubernetes has not really decreased, but definitely has not increased either. It's pretty stable since 2015, 2016, 2017. So the dates are wrong in this graph. It's actually 2016, 2017, 2018. But indeed, you can see that there is not really increase of the activity for Kubernetes, but the activity in general has increased because we're not using all the things like test infra, the website, and community, and cops. Those are the ones that have been increasing the most. But still, it is somehow not growing that much. And this is actually an interesting part, because when we saw this, there's a couple of things going on, right? One of them is the fact that this shows that the activity in the Kubernetes community is in maintenance mode, basically. There's not much more activity than before, but also it's not declining, which means that we're basically improving the code little by little, maintaining the quality and fixing issues, but not necessarily adding extra features, or at least not big ones. So when we mentioned this to the Kubernetes community, there was an interesting reaction to that, which was basically saying, there's no way this is true, right? And the interesting thing is that we were indeed missing stuff. So I think it's here that we have it. Yeah. So here is the analysis that we had, including 2018. You can see that in 2018, even that graph actually went down. So there's activity going on, and then all of a sudden the activity starts declining, which is kind of worrying. But if you look, this is because we're looking at only the github.com/Kubernetes organization. But if you actually look into all of them, including Kubernetes-6 and Kubernetes Incubator, you're going to see that from 2016 to 2017, there's actually a huge increase of activity of those projects. So the innovation has not really disappeared from the community at all, but rather it has been migrated into other places where you have the SIGs. So for those that do not know Kubernetes, they actually organize themselves into special interest groups, and they're going to be working on specific things. So for instance, external storage, Kube, AWS, all of those are, or cluster API, those are special interest groups. And then on top of that, you also have incubators where people are coming out with new tools, etc. Right? So if you add those, if you analyze those two, you're going to see that all of a sudden the activity starts to be not as in decline as we initially thought. Okay, so one more thing that you can do, and this is a pretty basic analysis. Since then, we actually do much more interesting analysis. But let's do an analysis of the contributors to Kubernetes, right? So here what I'm going to do is I'm going to find how many commits, so how many contributors we have per repository, and also how many commits they contributed, right? And this is going to tell us, so with a little bit of more maths, the interesting thing, wait, did the graph disappear? Oh no. Okay, I'm gonna try to run this, but probably I'm gonna have to go into the blog. Yeah, into the blog. Let me see. Unfortunately, yeah, that the result of that graph disappeared. And this should, now this could take relatively long because there's actually a lot of different commits over all of the repositories. So let me go back to the blog instead. To this one. And I will share all of these links later on so you can see them too. No, it's not here, unfortunately. Okay, so the interesting thing about this was basically we were able to identify those repositories that have many number of commits per repository, many number of commits per contributor, or very few. The idea here is that we were able to identify those projects that are pretty sticky. So meaning that once someone contributes once, they're going to be contributing continuously, versus when someone just sends a contribution and they're done, right? The idea was to try to analyze whether people were contributing often to the same project over and over or not. And we found out that it depends on the project. And some projects were, in average, very low. There was very few contributors. No, sorry, very few contributions per contributor. And it turns out that most of them were actually related to the documentation, right? So our thesis is that people were going there and contributing maybe a type of fix and stuff like that, like very basic contributions. But the interesting thing is that most of the time, those contributors were not contributing anywhere else. So it would be an interesting idea for Kubernetes, for the Kubernetes management team, to use this information to make sure that people that contribute to the documentation projects, they're also, I'm not going to say, there's a process for them to basically increase their contributions from just typos in documentation to something that could be more relevant in their interesting group, special interest group, contributor, what's the name of the thing? I already forgot. It's not contributors, incubator, sorry. So we could actually bring people to use other, to help in other projects too. Okay, oh, this actually worked. Okay, so it took 142 seconds, but it actually ended up running. So you can see a little bit the ones that have, there's definitely a clear correlation in between the number of contributors and the number of contributions, which totally makes sense. But there's also some of them that are somehow a little bit off, right? So kubectl, for instance, is one of these projects where lots of the people are actually sending many contributions. They're actually contributing, their number of contributions per contributor is pretty high. While if you go into Kubernetes template project, that's actually probably very few contributors. There's somewhere around 10, maybe 20 contributors in there, and they didn't contribute much each. It's around 5 per contributor. You can print kind of the same data, but in here, and see that the ones that have the highest most productive contributors are things like Node API, component base, where this is actually the opposite. That's a typo. So the least productive contributors, or the contributors sending the fewer contributions per contributor, are these ones: cloud provider sample, template project, Node API. So all of these are things that are pretty much either components to other projects, templates, or documentation. While for other ones, Kubernetes, for instance, or test infra are the ones that have the highest ratio in contributors. So in test infra, we have 20,000 commits get done by 500 contributors. And that's actually the highest one, with an average of 40 contributors per commit, 40 contributions per contributor. We're gonna skip this part a little bit. We can do other interesting analysis. So find, for all of the files that we care about that are in head, find what are the languages that we have, right? So this is going to count the current number of files, language that we have. Unsurprisingly, lots of Go. So you have basically 2/3 are Go, and then the other third is distributed around Python, YAML, Markdown, etc. What about the number of lines of code? You can do that quite easily too. Simply, again, as before, some lines instead of counting the numbers of files. And we have a very similar result. Python occupies a little bit more than before, but that's pretty much the same files. Okay, but what about, this is for head right now, but what about over time? Well, we can kind of do the same thing as before. So we're going to pass a commit. We're going to get all of the files in that commit, and then we're going to be counting how many files per language we found. When you do this, it's going to take a little bit longer, because indeed you are counting all of the repositories, all of the versions. So actually 73 of them, 73 points. And this is the number of languages that Kubernetes has used over time. And the interesting thing is that it actually goes down. So we started around 12 or so, went up to 35, and then went back down to somewhere around 24, 25. The interesting thing is, these points out to the fact that the Kubernetes community has evolved over time. And during that evolution, they've actually removed legacy code, which is very important for something that needs to be future-proof. This means that Kubernetes is able to evolve without having that much impact on the rest of the code. One of the examples in here that I'll show in a minute is one of the languages that disappeared was, for instance, Makefile. And we can see that by doing a slightly more complicated, more advanced matplotlib thing, where we're going to be showing all of the languages over time and their activity. So bright means lots of it, dark means none of it, right? So Go, you can see that it started having a lot of Go, and it just keeps on more and more and more. Python, kind of the same. But Python, the interesting thing is this Python here. All of a sudden, there's a lot of Python. And it's interesting because Kubernetes is bringing Go. So why would we have so much Python? If you look at the same time, you also have makefiles. And the makefiles are kind of increasing. You also have, wait, was it Python or was it, let's see. Yeah, so it was Python. You can see kind of the same idea here. There's too many languages in here to understand anything. So if we limit, for instance, to a given set of them, you can see that, for instance, this pick here corresponds to a lot of JavaScript, CSS, and HTML being added to repository, and then figuring out that this probably was not the best place to put it, so disappearing. This was probably documentation that was probably auto-generated, and it was then moved to a different repository. So you can see that quite easily. There's other peaks in here. So for instance, that brown in there is going to be Python. And this is an interesting one because what happened in there is not that Python was added, but instead that Python is also the language that we use for building Kubernetes, because Bazel, which is the language that we use, that Kubernetes uses, so there's a bunch of build files they're called. Bazel is actually a Python dialect. So we identified that at this point, Kubernetes migrated from having a bunch of different makefiles to moving to a different build system, which is Bazel. This was confusing for me for a while until Michael, which I think is in the chat, pointed out that this was correct and that Python is indeed a language that corresponds to what Bazel uses. We can do the same analysis also per lines of code, and it's basically the same idea. So it's not that interesting. This to JavaScript number of lines of code and how it appeared, then disappeared. Okay, so to finish, we're gonna do one that is a little bit more advanced, but this one is probably the coolest one that we have. We've talked a little bit about the size of the project, about the activity, about the contributors, but there is a thing that people tend to talk about Kubernetes, which is the complexity, right? How complex is this project? Is it getting too complex? And I tried to find a good way to represent that complexity, to find a metric that would proxy that complexity. And the one that I found that was pretty interesting was the number of public APIs, right? So basically, the number of public APIs is, in my opinion, a good proxy to the number of concepts that someone building things on Kubernetes should take into account. So how do we do that? Well, the interesting thing about this is that all of a sudden, it is not that easy to identify what a public API is. So what I'm doing is I'm analyzing all of the Go code. So this is why the language is Go. And then I'm going to extract from the UAST, I'm going to get the content, I'm going to parse it as needed, and I'm going to extract this thing here. This is for every function group, find all of the functions in there, because you can actually define many functions together in Go. That's why we have this concept. So for every function group, find all of the aliases and give me the identifier. So this what it's going to do is it's going to find all of the function names. And then from that node, extract the name itself. Then with a little bit of Python, because at this point, isUpper was not supported. I think that isUpper is not supported in the engine, so we could remove this and just say, count those for which the name starts with an uppercase letter, because that's actually how you say in Go whether something is public or not, right? So now what we have is something that given a commit, it's going to count how many public functions are in the Go part of the code base. So now we run this over all of the code, 73 points. That takes 9 minutes with 96 concurrent workers. With 2, that's going to take way too long. And then we can store those, indeed. But the interesting thing is that we can then pose them here. And this is the part where all of a sudden you see that Kubernetes during 2016 had this explosive growth between v.1.3 and v.1.4. We went from somewhere around 10,000, sorry, yeah, I'm gonna say 12,000 to 25,000 endpoints. If this growth had been continued, Kubernetes, in my opinion, would not be successful. It would have become too complex of a project. But luckily, not only the complexity was somehow stopped, you can see that the growth slows down by a lot, even though it's still growing a little bit, but it's growing to a more maximal pace. There's these drops in here. And these drops are very interesting because what this means is that we are breaking backwards compatibility, which does not correspond to the version in here, right? If you're removing endpoints, then you're breaking backwards compatibility, which means that this should be v2 dot something. Oh, yeah. So what is this? Why is this possible? Well, it's simply because Kubernetes doesn't count these endpoints as the ones that are the API, but rather the REST API. So while a lot of the code, and this corresponds to the number of lines of code and how it was disappearing before, while lots of code was removed, this actually moved to a different place, but it was not removed from the server. So the REST APIs are still there. So still, it's not backwards compatibility. It's not a broken backwards compatibility. You can see, yeah. So with that, this omitting staging is actually the way Kubernetes uses dependencies to, the way they put it there. And still, you can see kind of the same issue of that growth. Not as exaggerated because a lot of the public endpoints that were added were actually inside of staging. But still, there's that growth is a little bit concerning. And since then, it's been pretty much stopped. And I think that's pretty much it. One more thing is, okay, let's count contributors. So who is the one, what is the company contributing the most to Kubernetes? Not shocking, it's Google. But then after that, we have github.com, which corresponds to GitHub employees, but also GitHub users. Gmail.com, so github.com and gmail.com, I call those the people. They're basically contributors that are using their personal email. They could work for other companies, but they're not using those emails. And then you have Red Hat, Microsoft, ZTE, Huawei. Sorry about that. You can also do, I really like word clouds. So kind of a word cloud with all of the big names in the community. So yeah, Mesosphere and VMware and TOF and ZT, QQ, a lot of different Chinese companies in there too. And then we can do, there's actually one that I want to point out because I think it's pretty amazing that it's there. Somewhere in there, there's jessfraz.com. So as an organization, Jesse Frazel is there. And the other organization, which is also a person, it's somewhere, I cannot find it now, but there's betafamily.com. That is, oh, right there, quite big actually. So that is Joe Beta. So Joe Beta and Jesse Frazel, they appear as companies contributing because their contribution was so large. And then if you want to do it per person, you're going to see that there's a lot of people actually from no reply at github.com, right? So that is why we see GitHub as being a big contributor. If you say that you don't want to share your email, this is the one that is going to be shared. But then you have also Kubernetes production user and a bunch of different ones. And I also built a little word cloud with this that shows you a little bit who are the biggest contributors to the project, which is something that even if it's super simple to compute, it's always something, if you're thanking the contributors, showing something like this, it's always cool because people will look for their names in there. It's always a fun thing to do. I wonder if there's any questions. We have some minutes left. So if you have any questions, this is the time. We'll be sharing all of the links that I showed right after the meeting, so don't worry about those.
There's a comment from Michael, but no.
Oh yeah, Michael saying beta family. Yeah, we have beta family. We have jazzfraz.com. We have my previous employer. Actually, my previous employer was Google, but before that, we have Amadeus.com, which I hadn't noticed before. So yeah, there's a lot of different companies that are helping. A little bit of there's a kind of a cheat thing here. This is actually the logarithm of all of the commits. Otherwise, you would just see basically google.com and users not reply github.com. So by using the logarithm, I'm actually getting to see many more people, including Docker and things like Baidu, which are not a huge contributor, but after all, they actually are pretty important.
So if there are no questions, maybe people have ideas of how to improve or build on top of this analysis. We're always looking for suggestions. So anything that people are curious about, feel free to ask about it.
Yeah, also, if you're interested in a different analysis, if you go to so engine analysis on github.com/source/engine analysis, you will see that there's also a TensorFlow analysis that we added recently. And it's going to do slightly different analysis. There's a lot of different new things. We are using K clustering of the contributors to try to classify them into more of like front-end engineer, back-end engineer, etc. All of those things are things that you can actually analyze quite easily thanks to the engine and running some TensorFlow models on top. So I'll send the link to this repository and you can check both Kubernetes and TensorFlow. And if you have any interest on having some other community or some other repository analyzed, you can go for it and we'll be happy to review. Or you can also point it to us and we'll try to see whether we have time to build more analysis. This repository is going to be growing over time for sure.
All right. Well, one question. Okay. Have you thought of any technical debt analysis use case?
Yeah, so for technical debt, one of the things that we're doing is we are able to. There's a lot of different technical debt things, of course. Let me stop the video. No, so let me stop the share. So okay, so one of the things that we've done is find libraries that are not supposed to be used anymore, right? And keep track of where we're using them and how many we're using, and we're able to see how it is going down. Also, the things that you can do quite easily is, for instance, how much Python 2 are people still using in their repository, and how it's being migrated to Python 3 little by little. And you can actually see those graphs of that migration, and even analyze how many lines of code of Python 3 you are creating for every line of Python 2. Things like this are pretty useful. And it's actually a little bit of the idea of the engine, right? Like here, what we're doing is a posteriori analysis. Like I'm analyzing something, I'm telling you what happened. But the idea is that if you get this analysis and actually you want to predict the future, in our case, it's Kubernetes is premature, the growth is it's stopped in the main thing, but it's moving around. This kind of information right now, if it was something like at the moment in 2016 where we had that exponential growth, it'd be important for people to figure out, right? So if you're going through any kind of transition, going into, say, I want to migrate to the cloud, and I want to make sure that I don't have any more make files, and instead of the make files, we're using something else, and then we have our Docker images, and there's a Docker file per microservice and things like this. You can measure, you can add metrics and create pretty straightforward graphs showing where you are in the thing. So this is a little bit the idea behind, but yeah, going back to technical debt, it really depends on your analysis. Most of it is going to be doable because we're able to analyze dependencies and go quite deep in the code and extract specific things, but it really depends on the definition and exactly what kind of technical debt you're looking for.
We have another question. What's the largest code base that you've analyzed or is sourced?
I would say, so probably one of our customers, but we cannot really say their names. But other than that, I'm analyzing now the Go code in GitHub, which is a little bit too much. And it's not one piece of code. So probably the largest repository is either TensorFlow or Kubernetes. I'm actually not sure which was larger.
How about PGA?
Oh yeah, actually PGA, that's a great thing. Yeah, so we also have public Git archive, and we've analyzed public Git archive partially with the engine, not completely, but one of our goals is being able to scale to that level. And in there, you have all of the repositories in GitHub that have 50 stars or more, which corresponds to around 3 terabytes of source code. So yeah, that is pretty large scale. That's where we're trying to get. We're still not there, but we're moving quite fast towards that. Cool. And
yes, it's nice. One more question. Can we do code reviews this?
No, that is actually material for a different meetup. With the project that we're creating for code reviews is called Lookout, and you can find it on source.tech/lookout. And that is specifically for not monitoring what's going on, but actually avoiding new defects of entering your code base, right? So you have things like linters and a lot of different analyzers, and you can create your own also. It's completely open source. And some of those analyzers are actually even powered by machine learning. We can discuss that in a different meetup.
Nice. Well, I think that's it, and we're out of time. So thank you, Francis. Thank you, everyone, for joining. Have a good rest of your day.